Mark Rosengarten. Welcome to
Ask Rosengarten.
Hello and welcome back to Ask Rosengarten. Today we've got a couple of questions from Chad Ingham. Today's first question is, water is 11.2% by mass hydrogen. How many kilograms of water would contain 5.0 grams of hydrogen? Well, the first thing you need to do is find out how many grams of water would contain this many grams of hydrogen. And to do that, you use the simple formula for figuring out percents. Percent is equal to the mass of the part that you're interested in over the mass of the whole that the part is a part of times 100, with percent as a unit. Now, in this particular case, we happen to know the mass of the part, and we have this 100%. We're trying to solve for mass of whole. So let's do a little bit of algebraic rearrangement here. So in order to find out the mass of the whole sample of water, we first take the mass of the part, which is 5.0 grams, times 100, divided by the percent, which is 11.2. So this will equal 5.0 grams times 100 with percent as the unit over 11.2%. The unit percent cancels. And this means there are 44.6, well, that's 2 sig figs, so that's 45 grams of water. So if you've got 5 grams of hydrogen, and hydrogen makes up 11.2% of the mass, that means the mass of the entire sample is 45 grams, because 5.0 is 11.2% of 45 grams. Now, to convert that to kilograms is just insanely easy. There are 1,000 grams in a kilogram. So to cancel out the unit grams, you divide, and you get 0.045 kilograms. So you've got to take this one step at a time. You can't do it all in one shot. Now, the other option you could have had was to convert the grams to kilograms first, and then run through this procedure, and your answer would have been in kilograms. So there's more than one way to do this. The next question is very interesting, and I'm sure it's going to be one that you're going to worry about the next time you make a sandwich. You know, you have to worry about what you're going to put with peanut butter. You have it with jelly, you're going to have it with marshmallow fluff, you're going to have it with, banana. Either one of those options is incredibly delicious, but none of them have any bearing on this math problem. A jar of crunchy peanut butter contains 1.43 kilograms of peanut butter. If you use 8.0% of the peanut butter for a sandwich, how many ounces of peanut butter did you take out of the container? Well, this is actually a fairly simple multi-step problem. First of all, 8.0% is what we use, so we're going to take 8% of 1.43 kilograms. 1.43 kilograms times 8.0% over 100, okay, because that's how you take a percent. And what is 8.0 over 100? That's 0.08. All right, and so that gives us 0.11, that's 2 sig figs, 114, so that's 0.11 kilograms, a tenth of a kilogram of peanut butter. That's a fair amount of peanut butter. Okay, so 8% of our 1.43 kilograms is 0.11 kilograms. Now, it's actually easier to convert grams to ounces than kilograms, because I happen to know what the conversion factor is from grams to kilograms. You can look it up if you don't know. It's easy enough. Just go to Google. How many grams is there in an ounce? Easy. So what I'm going to do is I'm going to convert kilograms into grams. There's 1,000 grams in a kilogram. Kilograms is in the denominator, so I have to multiply to cancel it out. And that comes out to 110 grams of peanut butter. A pound is 454 grams, so this is about a quarter pound of peanut butter. That's a lot of peanut butter to put on a sandwich. Now, it turns out there's about 28.3 grams in an ounce. 28.3 grams per ounce. Now with grams in the numerator, we have to divide to cancel out grams. And this gives us 3.9 ounces. Well, 4 ounces is a quarter of a pound, so you can see my estimate was pretty dead on. 4 ounces, a quarter of a pound of peanut butter? Are you crazy? That's a huge amount of peanut butter. What are you doing? Don't you know what this stuff can do to your blood vessels? But it is chunky peanut butter, so I can understand. I guess the real question is, how much jelly are you going to use? But that doesn't matter for this problem. So once again, to sum this up, I take 8% of my original mass of peanut butter. That tells us how many kilograms of peanut butter we used. We convert that into grams, so I can use my conversion factor for grams to ounces to figure out how many ounces. Again, it's a multi-step problem, but if you understand conversions, then it's no big deal. I mean, if I asked you to convert seconds into days or seconds into years, you could do it, right? Because you know that a certain number of seconds is a certain number of minutes, and you can convert minutes into hours, and you convert hours into days, and you can convert days into years, okay? As long as you know the conversion factor, there's no end to how many conversions you can do. So using just one step, really rare. Today's final question is a very interesting one. Suppose you have two 100 milliliter graduated cylinders. In each cylinder, there are 40.0 milliliters of water. You have two cubes. One is lead, the other aluminum. Each cube measures 2.0 centimeters on each side. After you carefully lower each cube into the water of its own cylinder, what will the new water level be in each cylinder? And he continues to go on saying, I feel like the instructor is leaving out the formula to solve these equations. He thinks they might need density equals mass over volume. Well, actually, if you think about it, the fact that the cubes are made of lead and aluminum doesn't matter. The entire point of this question is so cool. You see milliliters? A milliliter is a unit of volume, and volume is a three-dimensional measurement, okay? Check this out. Let's say we have a cube, and that cube holds 1 milliliter of liquid. Do you know what the dimensions of that cube are going to be? The length will be 1 centimeter, the width will be 1 centimeter, and the height will also be 1 centimeter. Well, what happens when you take a centimeter times a centimeter times a centimeter? Well, that gives you 1 centimeter cubed, okay? A milliliter and a cubic centimeter are really the same thing. So when they say that the cube measures 2.0 centimeters on each side, this side is 2 centimeters, this side is 2 centimeters, this side is 2 centimeters. So all you need is volume equals length times width times height. 2 times 2 times 2 is 8, okay? So the cubes take up 8 cubic centimeters worth of volume. 8.0 cubic centimeters, being 2 centimeters each on each side. Well, since a cubic centimeter is the same as a milliliter, 8 cubic centimeters would be the same as 8 milliliters. So if the original volume of water was 40.0 milliliters, well, when you add the cube to it, since the cube has a volume of 8.0 milliliters, it'll cause the water to rise by 8 milliliters, right? Water displacement. So the initial volume is 40 milliliters. Your final volume will be 48.0 milliliters. You don't need density. The whole idea that I think was throwing you off was the use of these two different metals. Okay? Now, if the question had asked you, what would the mass be of each cube? Well, that's a whole different story, okay? But it's just asking, how much is the water's level going to rise? Well, that depends entirely on the volume, and it's totally independent. They could have said you have a cube made of wood or a cube made of plastic. It doesn't really matter. The only thing that matters is that a milliliter and a cubic centimeter is the same thing, and that's the concept that this question is designed to get you to understand. And finally, I got a question from someone who viewed one of my previous Ask Rosengartens. We did the stoichiometry, and I had liters, and I divided by 22.4 liters per mole. And this person wanted to know, well, why did you use 22.4? Where'd that come from? Why didn't you use formula mass? I mean, we're always supposed to use formula mass when converting to moles. Well, that's only used when you're converting grams to moles, okay? There's many things you can convert to moles. And in that particular problem, I wasn't just converting grams to moles, I was converting liters of ideal gas at standard temperature and pressure to moles. Now, if we assume that all gases behave the same, if we treat them as ideal gases, what we can say is that 1 mole of any ideal gas at standard temperature and pressure will occupy a volume of 22.4 liters per mole. It's known as the molar volume, okay? Grams will have their gram formula mass, also called their molar mass. You get it? Molar mass converts grams to moles, and molar volume converts liters to moles. Okay, so if you're trying to convert something to moles, you need to use the appropriate conversion factor. And since I had liters, I need to use the conversion factor for liters. I had a tremendous amount of fun today, guys. These were great questions. So it's time for you to ask me questions so that I can answer you. What are you waiting for?
Ask Rosengarten.